Hello, everyone. I'm just in time. People claim that being late for Italians is a stereotype. It's not. OK, so I would like to talk about data and AI and give you some insight about a different approach, which is inspired by the way biology works, which is bio-inspired. So the big problem today is data. We hear a lot about the comparison of data as a new form of oil, new form of energy, a new form of economy. It has been only a few years back when we were talking about kilobytes, and then a few years later we've been talking about megabytes, and then gigabytes, and then now we are talking about zettabytes and yottabytes. And if you think carefully, in the past 10 years, actually, every year we have been producing more data than all the data produced in all the previous years, all combined. So the question underlying this statement is all this big data sustainable? Is it scalable? And how AI is playing a key role? What is AI? AI is taking this data and extracting from this data information that enable devices, objects to become smarter. And more objects are connected. There will be more than 20 billion connected objects in 2020, more than 40 billion cameras. So how AI can grow in a sustainable way? AI is this new form of electricity which is getting everywhere, from our home to our car to our office to our favorite restaurant. Now the key question is about how we can scale the way we do AI, given the fact that, for example, when we look at this year, our electricity bill will probably exceed 500 terawatts. And 500 terawatts is the amount of electricity that is being spent, for example, in the country like Portugal. It's 5% of the entire electricity bill of the globe. And this is expected to double every 4 years. How we can scale that? But maybe the question to ask is, out of this old data, what is actually useful? What is real information? What is the valuable data that make device smart? And when we look at the statistic, actually shows that less than 1% of the data is what is valuable for a device to do AI, to take a decision. So why we do extra work? At Prophesee, we take this approach a bit differently because we have been looking at the way biology works. And if you look at the way the human eye works, it's a very interesting model for AI. When you look at me at this moment, actually your eyes, your retina, is not acquiring a full image and sending the image to the brain. They're acquiring only differential information, only what is changing in the scene, only the dynamic information. And this is actually, it has been demonstrated that only 0.1% of the data coming to the retina is what is then transmitted to the brain. So it's a very tiny amount. Nevertheless, we are able to take very fast decision extracting from a huge amount of information in reality. And this is very different from the way conventional cameras work. You're familiar with the fact that now if you take a video of myself talking with a camera, you'd acquire a huge amount of data because you'd acquire a video is essentially a sequence of images, acquire a fixed point in time, which has been a conventional paradigm since 1865, since 150 years, when an Englishman called Muybridge, a photographer in Palo Alto, did this fantastic experiment of putting a sequence of cameras one after the other, triggering these cameras at a fixed point in time, and then acquiring a sequence of images of a riding horse. Maybe you saw this picture, right? Because he was trying to make the point that the horse, when he's riding, is actually not touching the ground, but he also found out that when showing these images one after the other, he was providing the sense of fluid motion. While in reality, there is no fluid motion because there is a sequence of images acquired at a fixed point in time with 3 main drawbacks, in fact. The first one is that you acquire a lot of data which are redundant because they come from the background, which is static, so very few information in reality. And in addition to that, we lose information between frames because we acquire a fixed point in time. That's the reason why, in reality, the motion of the horse is not really fluid. And the third drawback is that because the exposure time is actually fixed, we struggle all the time to face situations where you have very dark and very bright part of the scene at the same time. Now, what we do at Prophesee is different because we get inspiration from the way biology works. So we develop a neuromorphic vision system which combines a vision sensor which mimics the eye and a new mathematical approach to computer vision and machine learning which mimic the way the brain processes information. And this leads to four main benefits. The first one is that we make each pixel in control of the acquisition process, and therefore we only acquire what is relevant, only the essence of the scene, by enabling essentially to get 10 or 1,000 times less data. And the acquisition becomes actually scene-driven. It's not anymore an acquisition which is artificially driven by the camera itself, but is the scene that is driving the acquisition. So we are making a correlation between the amount of information we need and the amount of data produced, right? Which is not the case with a conventional camera. Then the second aspect is the fact that we acquire extremely fast. So we acquire temporal precision of fraction of milliseconds because each pixel is independent. So there is not anymore this constraint of waiting a frame-by-frame acquisition. The third benefit is that because each pixel is independent and asynchronous, it's capable to adjust independently the exposure time. So we enlarge the dynamic range hugely. So we can face situations with very bright and very dark parts of the scene at the same time, and we can handle pretty well. And on top of that, because the acquisition is becoming event-based, it's triggered by changes in the scene, but overall the amount of power consumed is extremely low. And this approach is not fundamentally new. This approach has been researched for more than 25 years. It comes from the field of neuromorphic vision. And with the company Prophesee, we started industrializing this technology 4 years ago by initially serving application for vision restoration of blind people by connecting our silicon retina to retinal or cortical implants. And now we are deploying to any field of application where camera technologies are used for machine vision or for AI, in autonomous driving, in surveillance systems, in mobile and wearable devices. So we are entering this space of the big data problem where actually, if you think carefully, 80% of the data today are vision-based, are produced by cameras. And this trend, as we said earlier, is going to grow in the next years. And now, what I like to think is that a neuromorphic vision technology will help us to push AI closer to the edge. Because if we push AI closer to the edge, we will be able to, first of all, reduce the amount of data. So we will not need anymore to collect and process zillions of data. And in addition, we will be able to make device smarter at the edge of the acquisition. So all in all, I like to think the fact that, yes, we are indeed entering this new era of where data are becoming this new oil, new source of energy, new source of economy. And the AI is indeed becoming this new form of electricity. But I like to think, making always the parallel with the oil industry, that a new fundamental approach is needed to make this scalable and sustainable. And to this extent, neuromorphic technologies, the way biology works, is telling us that there is this new form of renewable energy for AI that is going to make eventually AI scalable and sustainable in the long term. Thank you.